Quindi, so welcome everyone to this new season of the Complex Analysis Seminar online. And it's my pleasure to have in a hybrid modality, Lomonaco from IMPA, who's going to talk about mating quadratic maps with the modular group.
Thank you very much. I think I kick it off. Thank you very much, Filippo. It's a pleasure being here. Bit difficult to arrive actually, but very happy to have managed. So today I'm going to tell you about a pretty long story. It started actually in the 90s, and it's a joint work with Sean Bullitt from University of Queen Mary, London, and it's about
You should mute your microphone, please.
And it's about mating quadratic maps with the modular group. So I will tell you first about quadratic maps, then about the modular group, then about what is a mating, and then what actually we mean with mating quadratic maps with the modular group.
Cominciamo. Michele, mi senti?
Sì.
Mi vedi anche?
Sì, così si vede.
Ok, grazie.
Okay, so if we consider a rational map on the Riemann sphere, and we start iterating this rational map, if this rational map has degree at least 2, because in other cases it's a bit boring, then the action of this iteration gives a partition of the Riemann sphere into completely invariant subsets. One is the set where the action is stable, tame, normal. So if we start taking, let's say we have a rational map and we start iterating it on all the points of the Riemann sphere. So we take a point, we take the image of the point, the image of the image, the image of the image of the image, and we see what happens. And we want to know if 2 points are nearby. Do they stay nearby forever? Are they friends? Or do they go far away? And it happens that this action of a rational map gives a partition of the Riemann sphere in the set where the orbits are stable. So if 2 points start nearby, they will stay nearby forever and ever. And this set is called the Fatou set. And the complementary, which is called the Julia set, which is chaotic. Technically speaking, the Fatou set is the set of points of the Riemann sphere where the family of iteration of the map is equicontinuous or normal on a neighborhood. So they all stay together, the points, they all travel together. And then there is the complementary Julia set, which is chaotic. We can take an example. If we consider the easiest rational maps are polynomial, and so we can consider an easy polynomial of degree 2, P0 of zeta is zeta squared, and we see that the set of points with modulus less than 1, when we iterate it, has modulus smaller and smaller and smaller and smaller and smaller, and they will all converge to 0, they are all friends. If they have modulus bigger than 1, the modulus will become bigger and bigger and bigger, they will all go to infinity. So the unit disk and the complementary are in the Fatou set. And the chaotic part are the points on the on the unit circle where the action is chaotic, and this is the Julia set. No, I don't have colors, it's fine. And this is the Julia set. Okay. The easiest rational maps, as we said, are polynomials, and the family of degree 2 polynomials after normalization can be put in the form zeta squared plus c, with c a parameter in the complex plane. And for every polynomial on the complex plane, infinity is fixed. Infinity to square the plus c is infinity, and it's attracting. If we take a point near to infinity and we square it, it's going to get closer and closer and closer to infinity. And it has a basis of attraction, which is the set of points that converge to infinity. And the complementary of the basing of attraction is the field Julia set, which is the set of points with bounded orbit, which in this example was the closed unit disk. And in the picture, I draw the Julia set for some elements of the quadratic family. Here you can see for c equals 0, here for c equal 1/4. If I move the cursor, do they see?
Yes.
Okay, here is for c equal 1/4. Here is for c equal 1/4 plus epsilon. This is for c equal -1. This is for -1 plus epsilon. And the first thing that you see is that some field Julia sets are connected and some are not. And the connectedness locus is the set of parameters c such that the field Julia set is connected, which is called the Mandelbrot set, which is this set. And as we said, if we are in a neighborhood of infinity, zeta squared is much stronger than the plus c. The plus c is not very important, and actually there is a conformal conjugacy between the action of your polynomial, quadratic polynomial, and the map z go to zeta squared. And if the field Julia set is connected, this conjugacy extends to the whole basing of attraction of infinity, so to the whole complement of the field Julia set. And this conjugacy, if the field Julia set is locally connected, the inverse of this conjugacy extends to the unit circle, and semi-conjugated, the action of zeta goes to zeta, to the dynamics of your polynomial on the Julia set. This is to say that if we have a polynomial, quadratic polynomial on the Riemann sphere, outside the field Julia set, the dynamics is the dynamics of zeta squared, and on the boundary, if your field Julia set is connected, the dynamics is zeta goes to zeta. The family of polynomials, polynomials are hyperbolic maps. A map is hyperbolic if it is expansive on its Julia set, or equivalently if the critical point is attracting to an attracting orbit. And outside, it's a big theorem from Fatou that the field Julia set is connected if and only if all the critical points are in the field Julia set. And with degree 2 polynomial, we just have one critical point. So either your field Julia set is connected, either your critical point is going to infinity. If your critical point is going to infinity, your map is hyperbolic, because your critical point is attracted to an attracting orbit. And it's a big conjecture that the interior of the Mandelbrot set is made of hyperbolic components. All the maps, for all the parameters in the interior of the Mandelbrot set, your polynomial is hyperbolic. now we consider the parabolic counterpart of polynomials, of quadratic polynomials on the Riemann sphere. And this is the family per 1, 1. From home, you will see it on the slides, but I will also write here because for the public is per 1, 1 in minor terminology, which is actually it's not a set of maps, it's a set of equivalent classes, conformal equivalent classes, where PA of zeta is zeta plus 1 over zeta plus A with A in C. Now, for every A, infinity is fixed, but this time is parabolic. It has an attracting direction and a repelling direction. But there is this attracting direction, so there is a basing of attraction, which is completely invariant, and we can define the field-Julia set in the same fashion as for polynomial, as the complement of the basing of attraction of infinity. Just this time is parabolic. And here I drew the field-Julia set for some elements. This is for A equal 1, and this for other parameters for which the field-Julia set is connected. And the connectedness locus for this family is called the parabolic Mandelbrot set M1, which is the set which the Mandelbrot set looks like this. And this is for polynomials. And the parabolic Mandelbrot set looks like this set. It looks exactly like the Mandelbrot set, but here is smooth. And this is the connectedness locus for this family. Actually, here we have classes. Here we have B, where B is 1 minus A squared, because P of A is conformally conjugated with P minus A, just interchanging the critical points. Okay, and these two connectedness loci are homeomorphic by a theorem of Carsten-Petersen and Pascal-Lefauche. And also in this case, we have a conformal model for the dynamics outside the field-Julia set. We read that in this case, the conformal model is given by the map Q0 of zeta squared, while here is given by the Blaschke product H of zeta squared plus 1 over 3 plus zeta 2, sorry, over 3 plus 1. And these two maps are topologically conjugated on the unit circle. This is to say that the dynamics on the boundary of the field-Julia set, if it is locally connected, is the same topologically. Okay, this will be very important later. Okay, now we leave for a little bit the world of iteration of rational maps, and we enter in a different world, PSL2C, which is the group of two matrices with complex entries and determinant 1. So the elements are Möbius transformations. And actually, we are interested in what is called the Kleinian groups, which are discrete subgroups of PSL2C. What does it mean? We take a bunch of matrices, a bunch of Möbius transformation, we compose them in all possible ways, and we see what happens. And the action of a Kleinian group also gives a partition of the Riemann sphere into completely invariant sets. There is a stable set, which here is called ordinary, where the elements of the group forms a normal family. So where the orbits go all together. The actual is stable. And the complementary is called the limit set. Actually, in this talk, we are really interested in just one a Kleinian group, namely the modular group, which is PSL 2 zeta, which is the Kleinian group with generators tau 1, which is zeta plus 1. Well, I can take this up, I guess, which is probably here. Technology is difficult. We're interested in the modular group, or PSL2 zeta, which is the group of 2 matrices with integer determinant, and is generated by, well, we can take as generators tau 1 of zeta, which is zeta plus 1, and tau 2 of zeta, which is zeta over zeta plus 1. What does it mean? That with these two maps, composing it in all possible way, we generate the group. And this gives a tessellation of the Riemann sphere. But since the same happens up and down, we just look at the upper half plane because we're a bit lazy. And the tessellation looks something like that. This is 0, 1, minus 1/2, minus 1/2, 1/2. If we take these to zeta plus 1, we fill everything. And if we start iterating by zeta, by tau 2 zeta over zeta plus 1, this reflects, and you start seeing something like that. And then again. Okay. Now, these two words, the words of a rational map acting on the Riemann sphere and the word of finitely generated Kleinian groups, this is Kleinian groups where the generator are a finite number, are much more similar than what it looks from far away. And actually it was Sullivan, the first one who realized that in the end of 80s, beginning of the 90s, making what is called the Sullivan dictionary, which is a dictionary between rational maps and Kleinian groups. Here we are just interested in the first two entrances. In both cases, the action gives a partition of the Riemann sphere in a stable set, which for rational map is called Fatu set, and for Kleinian groups is called ordinary set, and a messy chaotic set, which is the complementary, which in the case of rational maps is called Julia set, and in the case of Kleinian groups is called limit set. By the way, in the case of the modular group, the limit set is the real line, and the ordinary set is the upper half plane, also the lower one, but since it's the same, we just consider the upper one. Okay. So these two words are not so different. And actually, there exists an object which can be both. But since a map is not a group and a group is not a map, this thing has to be something more general. And here we enter in the world of holomorphic correspondences. What's a holomorphic correspondence? A holomorphic correspondence is a multi-valued map defined by a polynomial relationship. In this talk, we are just interested in two holomorphic correspondences. What does it mean? It means every point has two images and every point has two co-images. And then we iterate this thing and it becomes a mess at the third iterate and you want to cry, but there is a way to understand these things, I promise you. So, correspondences are a multi-valued map defined by a polynomial relation P zeta W equals 0, where the polynomial has degree 2 in zeta and degree 2 in W. So the 0 of a polynomial in degree 2 in two variable defines an algebraic surface, call this S, which is this. And then we can consider the projection on the Riemann sphere where zeta lives, the projection on the Riemann sphere where W lives. Could you see from home? Because I'm using also APA. Okay. Can I make the same draw on the computer? Ok. No, just this draw perché altrimenti è incomprensibile la cosa.
No, forse più bene.
Ah, ok. Qua la devo fare, ok. Cancello e ricomincio.
No, ti sposto io.
Ah, grazie. Ok, so, grazie mille. We have this algebraic surface, which is the 0 of these two polynomials. We consider the projection in the Riemann sphere where zeta lives, the projection in the Riemann sphere where W lives, and the correspondence, the holomorphic correspondence, is this association. So, for each point here, for each zeta, there are two W that kills the polynomial, right? These are the images. For each W here, there are two zeta that kills the polynomial. These are the pre-images. And iterating, you look the image and you keep going. So this thing really, it's a mess. So why am I telling you about this mess? Well, because we can write a rational map as correspondence, just taking as let me see if this is, yes. Just taking as, if my rational map is R zeta, which is P of zeta minus over Q of zeta, we just take as polynomial, as F zeta W, zeta W, defined by the polynomial P zeta W, which is W Q zeta minus P of zeta. And similarly, if we have a Kleinian group with generator, well, in this case, we just care about these two, we can write it as correspondence by taking the polynomial, the product of the two polynomials that kill these two terms. Okay? So these things are messy, but we can write a group as a correspondence and a rational map as a correspondence. And now the question is, well, a correspondence can be a rational map, can be a group, can be both together. And this question started to be investigated in the 90s when Sean Bullitt and Chris Penrose started plotting limit set of a family, a particular family of holomorphic correspondence, which I will present you later, and started seeing limit sets as the one you see here in the picture. And this looks like two copies of a Field-Juliet set attached together, and outside the tessellation of the modular group. The picture is something like and here you see something like which is kind of this tessellation outside. This is what seems the picture. And so they start thinking, well, can a correspondence behave like modular group and a quadratic polynomial or a rational map at the same time? In technical terms, can we mate a map and a group in a correspondence? Well, I will tell you now what I'm making here is. very roughly speaking, a mating between two objects A and B is an object C, which behaves like A on an invariant subset and as B on the complement. We have both dynamics. And matings exist in the world of polynomials. Actually, there are very nice videos and pictures on the page of Arnaud Cherita about matings of two polynomials. You can mate two polynomials which are mateable, you end up with a rational map. And matings exist, actually started in the world of Kleinian groups. So, can we mate a map and a group? This is the question. And Sean Bullitt and Chris Penrose, seeing these pictures, believed yes, and they gave a definition of a mating between a map, a quadratic polynomial, and the modular group, which is a 2-2 correspondence, holomorphic correspondence. And this is because if you want to write the modular group as a correspondence, this is a 2-2 correspondence. So if you want something that in an open set behaves like the modular group, you better keep at least the 2-2. So a 2-2 correspondence such that there exists an open set where your correspondence is conformally conjugate to the generator of the modular group, and the complement is compact and is the one-point union of two sets, one where your correspondence restricted here behaves like a quadratic polynomial, is hybrid conjugate to a quadratic polynomial. This is quasi-conformally conjugated and conformally on the interior. And on the other set, where your correspondence is restricted here is conjugated to the inverse of a quadratic polynomial. And the definition made sense looking at the picture. And then the question was, do this guy exist? Are there questions till now? Because I'm not sure if I'm going very fast or very slow. So far, so good. So, do this mating exist? This question has two sides. Is it possible to mate quadratic maps, polynomials, and the modular group? This means, do the dynamics fit? Is it the same dynamics on the boundary of your Julia set of a quadratic polynomial and on the limit set of your group? And does it exist some correspondent that could realize this? And then if we answer yes, then we have the other side. Okay, do we find, is there exists a family of correspondences such that every member of the family is a mating between a quadratic map and the modular group? And if the answer is yes, then we can ask, is the connectedness locus of this family, this is the family of parameters such that the limit set of these guys is connected, homeomorphic to the Mandelbrot set or the connectedness locus of your family? Which means, does your family organize internally as maps? And the first side of the question has been solved by Sean and Chris, and I will tell you briefly the answer. I enter in the second part. So, well, you probably guessed, since I'm here telling you the story, that yes, we can meet quadratic maps and the modular group. Actually, there exists a map, which is the Minkowski map, which is a homeomorphism that sends a number written in continuous fraction expansion to its binary representation. And this homeomorphism conjugates the action of generator of the modular group, this is 0, sorry, on the negative Ah, sì. Grazie.
No, però devi togliere...
Ah, devo togliere qua, ok. Io clicco qua. Tecnologia, portami via qua, ok?
Ok, così riesco.
Perfetto. Scusate da casa. So there is this map, Minkowski map, question mark, that conjugate the action of the modular group on the negative real axis with the doubling map. X goes to x, and to the halving map on the positive real line. So x goes to x divided by 2. And if you remember, the first thing I told you about polynomials is that outside the field Julia set, we have the basing of attraction of infinity, where the action of your polynomial is given by the map zeta square. And on the circle, the modulus is always 1, so you double the angle, so you have this map. I'm lying here, it's much more complicated, because if you take zeta plus 1, between it sends minus infinity 0 to minus infinity 1. So actually there are 6 commutative diagrams, but for the sake of this talk, it's conjugated. So in theory, the two actions fit. So morally, here we could attach a field Julia set of a quadratic polynomial, and here we could attach the field Julia set of a quadratic polynomial with the action of the inverse quadratic polynomial. It fits together. And actually, Sean and Chris did this topological construction, is in the first paper on this, making quadratic map with the modular group. Is 94, I think. But yes, it's possible. The dynamics fit. And then we have the second question, which is there a family? Qua va bene? Okay. Is there a family, how you say, a possible family where this mating could happen? And yes, there is, and you see, is the family given by this expression, which I won't even try to say in English, just read it, please. And this is a theorem from then in 94, that the matings between quadratic polynomials and the modular group lie in the family of quadratic correspondences given by this expression. I could explain how they got there, but it will take me a while. The short answer is that you look how the modular group acts, and it satisfies some relations. And if you want it to be conformally conjugated, it's better that you keep satisfying these relations, and you make some computations, and you end up with this form. If somebody's interested, I can explain it at the end of the talk, but I won't explain it here because it's a bit technical. Okay, and here below, I drew the limit set of some members of these families. Well, I will define what is the limit set next slide. So for each member of this family, it happens, if I draw here, they see me, right? Because it's still, okay. No, it's here, doesn't matter. No, I can keep it here. It's just that I wanted to do it for you and them at the same time. So yes, I will. Ok, sì, no, ma vedono ancora lì, vero?
No, aspetta, devo fare così.
Devo toccare 2 volte. Ah, solo toccare 2 volte, va bene, facile. In teoria sono una millennial, ma insomma, nella pratica un poco meno. Ah, something important that I forgot. Remember that on the boundary, the map that encodes the dynamics of a polynomial outside the field Julia set is zeta square. Outside the maps, the parabolic counterpart of polynomials was that Blaschke product, but on the boundary they were conjugated. topologically. Why I'm saying this? Because we could have started, instead of polynomials, directly with these parabolic maps, which is what they should have done. But polynomials are more famous, so you usually go there first. So, voila. For each parameter, your correspondence has a half plane where it behaves like a 1-to-2 maps. It maps these half planes inside itself and inside itself and inside itself. And you can define the forward limit set as the intersection of all these images. Something here.
Right.
Okay. And in the complementary, there is an involution, actually. This is how they arrived on this form, because you can write the modular group as an involution composed to a covering correspondence of a cubic polynomial. But I mean, there is an involution. And here, your map, your correspondence behaves as a 2-to-1 maps. So it sends the pre-image of these half planes to the half plane. Here is 2-to-1. Here is 1-to-2. And then there is the involution 1-to-1. And we end up with something to do. And the backward limit set is the set of pre-images of the half plane. And then by construction, here you have a parabolic fixed point, because here you're entering and here you're going out. So for each member of your family, you have a parabolic fixed point with modulus 1. And here you can see several limit sets for this family. Most of them connected, the fifth one is disconnected. And on the side, you see the connectedness locus, which is the set of parameters such that the limit set is connected. And you can see that it looks like the Mandelbrot set. Just instead of a cusp, it has a point. So the conjecture is natural, which is the family. This family of correspondences contains a mating between the modular group and quadratic polynomials. We connected the Julia set, every quadratic polynomial, and moreover, the connectedness locus is homeomorphic to the Mandelbrot set. And since the conjecture that was in 94, there has been a lot of partial results. And actually, they proved that there exists a mating between the modular group and the quadratic family, QC, for a large class of C. But they never managed to get all of them. Why? Well, because when you want a polynomial, you usually use something which is called polynomial-like mapping. And for doing this, you need to break the parabolic fixed point. So all these proofs were done in the same fashion. You take your correspondence, you perturb in order to break the parabolic fixed point. So, so you have, as you can see here, the limit set disconnected. You apply polynomial-like mappings, which is a technical tool in order to end up with something which is conjugated to a polynomial. And then you come back, pinching. And yeah, you can do it, but I mean, your family has a persistent parabolic fixed point. Everybody in your family has a parabolic fixed point. So maybe you should think about dealing with the parabolic fixed point. Also, if you think about that, the modular group is pretty parabolic. I mean, look at the generators. So the idea is maybe parabolic goes with parabolic and hyperbolic goes with hyperbolic. And then is when I entered the picture and I started wondering, do we have a family of quadratic rational maps with a persistent parabolic fixed point? Yes, the family per 1, that I present you before. And so, which shown, we defined a mating between a rational quadratic map of the form zeta plus 1 over zeta plus a and the modular group as a 2-2 correspondence. The definition is the same, such that you have an open set where the dynamics is conformally conjugated to the action of the modular group, and in the complement, on the backward limit set, on a doubly pinched neighborhood actually of the backward limit set, you are hybridly conjugated to the dynamics of a member of per 1 on a doubly pinched neighborhood of its Julia set. And since there is an involution between here and here, when you bring home the backward limit set, you brought home also the forward limit set. And the result is from last year. Well, actually, it started 11 years ago, but it got published finally last year, is that for every A in the connectedness locus, the correspondence FA is a mating between the modular group and some rational map in the family per 1, some map zeta plus 1 over zeta plus A, with A in the complex plane. And here you can see in slides 20 an illustration of the theorem.
Can you characterize between the map and the element of the modular group, given one which is the other?
I don't understand. Characterize. I don't understand.
In the sense that you have the mating when you choose this A between an element in the modular group. And
the modular group outside, you always have the modular group.
Yes, but I mean, this element gamma and one directional map.
The rational map change. Outside, you always have the modular group. The rational map changes, and it depends on what correspondence you start with. Yes, you see in the picture, upstairs you have the parabolic Mandelbrot set and 3 Julia set. The first one is the center of the main hyperbolic component. So the first guy lives here. The second one is the center of the period 2 component, so lives here. And the third one is the center of the period 3 component, so it lives here. While downstairs you have what we call the modular Mandelbrot set, because it's the same thing, just outside you have the modular group. And you see the first guy is the center of the main hyperbolic component, and you have a pinch neighborhood of the backward limit set, which is the piece on the left, where your action is hybrid conjugate to the action of the guy upstairs on a doubly pinched neighborhood of the Julia set. The second one is the center of the period 2 component, so he is hybrid conjugate to the guy upstairs. The third one is the center of the period 3. So yes, you can. But outside, you always have the modular group. You always have the same thing outside. With polynomial, outside you have zeta squared. With per 1 outside, you have the Blaschke product that I wrote before. And with these guys outside, you have the modular group. And, well, the theorem works for members of the family with connected limit set, because for proving that outside you have the modular group, we start by the Riemann map, and then you really need something connected, because in other case, step 0 doesn't work. But it induces a map between parameter planes. You start by a quadratic holomorphic to two correspondents of this family with connected limit set. And you have somebody, a member of pair 1-1, hybrid conjugated. And then you can prove that this member is unique. And this is easy because it's basically a Riemann lemma. But this induces a map. So we have a map chi between M gamma, that we called the modular Mandelbrot set, and M1, the parabolic Mandelbrot set. And what we finally proved this year is that this map is a homeomorphism, which is dynamical. It means if I send A to B, because let's remember that in the parabolic Mandelbrot set we have B, which are equivalent classes. B is 1 minus A squared. From A, I'm going to B. Then the correspondence FA is hybrid conjugate on a pinch neighborhood of the backward limit set to the map PA, zeta plus 1 over zeta plus A, where A is given, where B is 1 minus A squared, on a pinch neighborhood of its Field-Julia set. And it's conformal on the interior, and it extends to homeomorphism between pinch neighborhoods. There is the extension works on a pinch neighborhood of your connectedness locus, because the root gives problem. We have homeomorphism between the whole connectedness locus and the whole connectedness locus, but the extension works in pinch neighborhoods, but it embeds on the plane. And this, together with the fact that the theorem from Carsten Petersen and Pascal Hoche that the modular the parabolic Mandelbrot set is homeomorphic to the Mandelbrot set, solves the conjecture. In the sense, the modular Mandelbrot set is homeomorphic to the Mandelbrot set, but to construct it, you have to pass through the parabolic Mandelbrot set. And looking the picture is obvious because you go between something like that to something like that to something like that. Okay. And while we were doing this, we also ended up with a dictionary between, well, we also described dynamically, we gave a complete dynamic description of this family, which parallels completely the dynamical description given by Douady and Hubbard of quadratic polynomials. And again, quadratic polynomials because they are more famous and there are more things written about them than about pair 1-1, so this is the logical model. In the case of quadratic polynomial, you have a Butcher map that uniformize the complement of your Field-Julia set to the complement of the unit disk, conjugating your polynomial with the leading term. In our case, we have our Butcher map that sends the complement of your limit set to the upper half plane and conjugate the action of your correspondence to the one of the modular group. Then, in the case of polynomials, there are things called external rays that are extremely useful for proving an insane amount of things, which are nothing more than the preimage. Well, let me make a picture for people that stay at home. No, stavolta ce l'ho fatta. Forse no. Okay. So if we have the Field-Julia set of quadratic polynomial, this is the 1 of zeta squared plus 1/4, just for an example, we have the Butcher map that sends the outside to the outside of the unit disk and conjugate conformally the dynamics. And we can take rays with constant arguments in the model and pull them back through the vector map. And these are called external rays. And it happens that external rays, if are periodic, they do land. And that repelling periodic points, no, this is parabolic actually, the only one that I couldn't take, are landing points of external rays. Now, in our case, we have the same thing. Yeah. In our case, we have our vector map that sends the complement of the limit set to the upper half plane. Well, we could have taken the complement of the unit disk. It's just that the modular group is usually in the upper half plane, so this was the logical setting. Conjugates conformally the dynamics, and on the upper half planes we have geodesics. So we can pull them back through our vector map, right? And periodic geodesic lengths. And repelling periodic points are landing points of geodesics. This was extremely difficult to do. This actually was inspired very much by a theorem of Anna Miriam Benini and Lubitsch. Very beautiful. And external rays are very much used in order to prove what is called the Yokot's inequality, which I won't tell you what it is because it's kind of complicated, but tells you.
So, what do you mean exactly by periodic geodesic?
Geodesics that come back. Show the action. You take a finite ports of Taiwan and Taichu, and then they come back.
Okay.
Period. Yes. Just that, yeah. Here we have two generators, right? So it's periodic. Try to whatever number of you take Taiwan, Taichu, ta, and then it comes back. And then if you pull it back, it lands. Periodic in this sense.
So they're not geodesic for the Poincare method, geodesic in another sense.
No, if you take a word in Taiwan, Taichu, you consider what are the you have one fixed point, you end up with, well, you compose, so you end up with a Mobius transformation that has two fixed points. One is attracting, one is repelling, and the geodesic is the one connecting the two. That goes out from one side, goes in on the other side.
Ah, okay.
And you move it,
you take the quotient with
and it comes back, see.
So what you're doing, you're taking the geodesic in the upper plane for
yes.
the Poincare metric,
and you pull it back.
You take the quotient with the group, and then this create possibly periodic geodesic, and that's what you get, right?
Yeah, making picture about that it will open, but I mean, I can.
I understand.
Okay, because it's technical. Everything is technical. I mean, this was 10 years of work, 3 papers, big, the 3 of them. So I mean, it's and based on another paper that was pretty big. So I mean, it's a very long story. But yeah, the last thing that I wanted to say, really much, I can say a lot more, but this is the last thing that I really needed to say, is that, yes, there. But if I do it always here, they see it, no? They keep seeing it, or not? Okay, whatever. Using the fact that every repelling periodic point is a landing point of a periodic geodesic, and a lot of other facts, because I mean it's a pretty deep result. Yokot's proved what is called the Yokot's inequality, which is an inequality that tells you how much a point can be repelling and how much has to, how much the multiplier can rotate and can be repelling, depending on where the point is on the Mandelbrot set, which has as a consequence that the sides of these are called the limbs of the Mandelbrot set, the things attached to the Mandelbrot set, are bounded, have a maximum size. And there is compared to this guy, there is a relation between this guy and this guy. And we have the same result in our case. And actually it's better, we have a stronger Jacobs inequality. If you see the formula, but I don't want to start speaking about formula again because it's, which means, and you can see from the picture that these guys shrink more with respect to this guy than this guy with respect to this guy, becomes smaller. Unfortunately, this just works for the first level limbs, because then you can, here there is another one attached, and another one attached, and another one attached, and and the methods that gives a stronger estimate use just work for the first one, because then, of course, the dream will be to say that this guy is locally connected, because now we have a homomorphism. So, but so far we have this string.
Proving the MLC, let's say, conjecture for the modular group is as difficult as the original one.
We have something better at this point, but the method we used in the first point doesn't work with this one. But the modular group is much more rigid than zeta square. I mean, it's very rigid. So I mean, my dream is finding something like that. Of course, I mean, we can dream, no? But it's not something that I would say work in progress or anything like that, because no. But dream, yes, I dream the dream. And well, it's already 6. I'm not sure I bother you with the ideas of the proof or, I mean, these are the results and this is what I really wanted to tell you. Then, so let's do something like that. Let's thank you for your attention. And then if anybody has question about how, what, whatever, I can answer, because it's pretty big. Thank you very much.
So, thank you very much, Luna. And other question from home? Nicola, you want to say something? No, you have to unmute the microphone. Okay.
I don't have anything to ask.
Sorry, I didn't get. No, okay. Seems Nicola is nothing. So we thank Luna again.